All right. Let's take a look at what we've talked about with chapter 1. On number 1, it says describe the discontinuities of the graph. Now I'm going to kind of, as we go, tell you where you'd look if you need more help. Discontinuities came from lesson 1-3. And the problem I've given you is what's called a piecewise equation. Piecewise came from 1-1. So I'm tying together multiple lessons, and I'm going to do that mostly this afternoon, is I'm going to continue to tie in multiple pieces together. So on this problem, it says describe the discontinuities. And so before we do any algebra or I show you in a graph, I just want to remind you the 3 types of discontinuities we can have. Infinite is the discontinuity that exists when the graph breaks from a visual standpoint, breaks and goes to infinity at the break. So there's 2 pieces of blue graph. So to have 2 pieces, what had to happen somewhere in the middle? You have 2 pieces of graph. That implies the graph starts with the B, rhymes with broken. Broken. It was broken in the middle. Yeah, it was broken in the middle. So you can have infinite when it breaks and goes to infinity. You could have removable when it looks like it's one connected piece, but there's just a little hole that actually separates the 2 pieces of graph. That's removable. And then there's also another one called jump. And that's when the graph literally jumps from one place to another and continues on. I thought of an illustration earlier this morning. You remember Buzz Lightyear in Toy Story 1? I know you guys weren't even born when that came out. It's embarrassing that I'm getting that old. But when it came out, Buzz Lightyear had a saying that he would say to infinity and beyond. And he was implying something that no other toy could do that he could do, that he could just take off and fly wherever he wanted to go. Now, for everybody else, we called it falling with style or just jumping. For him, he could take off and go to infinity, so he thought. But for all of us, if we tried to jump off the ground, guess what's going to happen? Come back down. We're not going to go to infinity and beyond. We're going to land somewhere else. Now, we might be able to cover some space, like a jump here. I can cover some space, but I'm not going to take off and go to infinity. So just to define that, to show you the difference, a infinite is when it breaks and literally goes to infinity and beyond. A jump is like a normal human being. We left at one spot and we came down somewhere else that's not infinity. That's a jump. Removable, it looks connected at first visually, but there's a little hole between the 2. So after reviewing all that, let's do algebra first. If we want to describe the discontinuities, algebraically, what you're looking for is piecewise or division. Those are the 2 things you look for, piecewise and division. That's what creates breaks. A jump can come from a piecewise. So this is a piecewise equation. It has multiple pieces. Here's piece number 1. Here's piece number 2 by equation. I should say equation number 1 or expression number 1, expression number 2. We also can call these branches, branch 1, branch 2. So here they are. There's 2 branches. How you determine if it's a jump when you see piecewise is you type in, I say type in, we mathematically compute by plugging in the domain value given. So this domain value here is 1. The domain, remember, X means domain. The domain value given is 1. So if I plug it in, I know it looks like an H, it's an N, domain. We plug in the 1. We'll find out if it's a jump or not. So let's do that. So every X, I'm going to plug in a 1. So for the top expression, 1 minus 1 is 0. On the bottom, 1 plus 12 is 13. 1 divided by 13 is 0. And now I'll go down below. According to PEMDAS, do I say -1 first or do I square first? Do I say let's take negative of 1, then square it, or do I say square the 1, then take the negative? Good guess, but it's wrong. According to PEMDAS, we need to square first. So 1 squared is 1. Make it negative, -1. If you had to do it the other way, they'd have to do a parenthesis, by the way. Then it would become a positive. But this is going to be -1 because 1 squares 1, make it negative, -1. So -1 plus 3 is 2. Are these different values?
Yes.
Yes. So this will have a jump discontinuity at, whoops, X equals 1. When your domain is 1, we have a jump discontinuity. How do we know? Because these two numbers do not equal each other. Because 0 does not equal 2, it's a jump. That's the way jump appears. Technically, there is one other way it can appear with greatest integer functions, but we're not dealing with that. So you just need to look, is it piecewise? Do they equal each other? Answer is no, so it's a jump. Now that's jump discontinuities. The other type of discontinuity comes from divisions. What is the rule about division that you're not allowed to do in mathematics? Where do things break down?
You can't divide by
0.
Yeah, the Zoomers know the answer, but there's a lot more Zoomers in fairness. There's something you're not allowed to divide by. 0, there it was. Okay. You're not allowed to divide by 0. So technically, we would usually, when we do domain, say cannot equal 0. But I'm not finding domain, I'm finding discontinuities. You'll learn discontinuities are the exact opposite, basically, of domain. So I'm going to leave it as equals 0, because that's where we have a problem. And so when I solve this, I would subtract 12 from both sides, and we get x equals negative 12. Now you might be wondering, why am I writing it all the way over there? I'm going to write what type of break it is. This problem, does this x plus 12 get canceled with the numerator? Are they the same factor or are they different from one another? Is x minus 1 the same thing or different than x plus 12? Are they exactly the same or do they look different? They're different. So if they're different, they don't get canceled. This stays there forever. And a synonym forever is infinite. We have an infinite discontinuity at x equals negative 12. So that's how you do this with algebra. Now, let's check this out. I know it's frustrating that wrestlers are loud next door, so hopefully the Zoomers aren't picking up too much of that, but yeah, you're going to hear that in here. It's frustrating. This said look at the graph. So should we look at the graph? Do you want to see what this looks like graphically? Let's start over and do this graphically. I have this graphed already for you here. Oh, no. Here. Maybe. Let me refresh my page. I thought I had it. No. Okay. Yeah, saved the wrong way. Let's zoom out so you can see what I want you to see. There we go. This is more of the picture I want you to see. How many pieces of graph do you see when you look at this graph? 3 pieces. So 3 pieces imply how many breaks? 2 breaks. There are 2 breaks to create 3 pieces. We list breaks by x values. So if you're looking on your x-axis, I see that there's a break on this x value. If you notice it going up and going down, we have a break there. So I'll just say at this x value. And also the graph breaks at this x value right there. So this one, that's negative 10, that's negative 15. So what value is in between 10 and 15, or 2 blocks over from negative 10 towards negative 15? Negative 12. Negative 12. So we have a break at negative 12. Now if you looked at the graph, where does the graph appear to be going? Infinities. So if their graph's breaking and going to infinities, whether positive or negative, doesn't matter. We would call that a infinite discontinuity. And so that's where that algebraic dividing by 0 graph came in right there. And now this was our jump. Do you see how this, let me zoom in a little bit. It's going to mess up my writing. But right here, let me just clear the writing. We have a jump. The graph was at this spot, and it jumps to this spot. And I can't remember, let's see, the closed dot should be with the first one and the open circle with the second. Technically, this graph should go away. Thank you. Open there, close there. And I know that because this is the first expression that has the equal to, less than or equal to, so it would be a closed dot. The second expression had the open, greater than, so it would be an open circle there. That's a jump, and that's how it would look at. That would be a jump at the x value of what's in between 0 and 2? 1. So at x equals 1, we have a jump discontinuity. That's how you do that visually. All right, now that was one problem like that. But in my other classes, I've had a lot say, hey, can you show me that again? So I'm going to actually add something that's not there. I'm going to just do an extra problem. So next thing you can write down here, insert. Let's just say, what if this was your problem? G of x equaled x minus 3 of x times x minus 3 times x plus 1. Let's say this was the problem. And as you are copying down this equation, I'm going to ask a question. How many types of discontinuities are possible? How many types do we have? 3. They are infinite, jump, and removable, I hear. In that order. That's the way I heard it. On this problem, is this equation a piecewise equation? Multiple pieces? No, since it's not piecewise, which of the 3 can I eliminate from my choices? Which is created by piecewise?
Jump.
Jump, thank you. Jump. It's a jump. So it jumps out. There's no piecewise, so it can't be a jump. So it's either infinite or removable. What's the rule about division, specifically with dividing by a certain value? What are you not allowed to divide by? 0. So in this problem, there are 3 x's. There are 3 possible values I'm not allowed to divide by. Now I want you to look closely at this problem. One of these 3 factors is different than the other. Which one's different? Okay, this one I see, it doesn't have a number with it. We can consider that different. But there's this something else I'm looking for, and it has to do with the numerator. Which one of these 3 stand out because of the numerator? The middle one, x minus 3. Because what can I do with this x minus 3 and this x minus 3?
Cancel it out.
I hear cancel it out. How about remove it? Can I say remove? That would be a good word. Now, why would that be a good word? Because that means it's a removable discontinuity. That's where it gets its name. We remove it from the problem. We canceled it, simplified it, whichever word you want to use. We have a removable discontinuity at x equals 3. And if you're wondering why is it x equals 3? Because again, you're not allowed to divide by 0. And since these are all multiplying, what you would do is you'd say x minus 3 equals 0. And when you add the 3, guess what we get? X minus 3. Now, if you watch your lessons from 1 to 5, you would also know that I always say inside lies or x's lie. That's why we break up with the x's, marry the y's, right? You break up with your x's because they're always lying to you. So instead of being minus 3, it becomes a positive 3. Okay, that's a removable. These 2 factors stick around forever. What's a synonym for forever? Infinite. So we would have infinite discontinuity. And I'll say discontinuities, because there's 2 of them, at, if x is by itself, it's just a 0. At x equals 0, and what does this one become? -1. And so if I graph this, I don't think I have this typed in, so I'll need to type it in real quick. Am I okay to switch for graphs or switch images? Anybody still copying? Okay, if I looked at the graph, was it x plus 3 or x minus 3s? I've forgotten. It was x minus 3s. And then x plus 1. Okay. If we look at this, you'll see there are 2 infinite discontinuities. We have an infinite discontinuity here. That's at -1. It's in between 0 and -2, so that's at -1 like we said. There's another infinite discontinuity here where the graphs are breaking and going to infinities at 0, just like we said. But remember, we found another one. We found a removable. Removables fail what I call the eye test. So the eye test is like using your eyeballs. You look at it, you can see those 2 really easy. Let me put this x equals -1, stay consistent. Okay, so those infinites are real easy to see, and jumps are easy to see. What's difficult to see are removables. What you'd have to do is either click the graph and drag this solid line. If you notice, I'm dragging it, it's a solid line, and get to the spot. And then once you get to the spot, it'll go open circle. There it is. Boom, undefined, open circle. You could do it that way, or probably the easier way is just click table. So I hit settings, and I'm going to hit convert to table. And when I do that, anytime you have an undefined, that means it's a break of some sort. If I type in 3, it's undefined. And so it's telling you there's a break, but you don't see it. So if you don't see it, it's a removable. It's been removed from the problem. There it was, but we removed it. We canceled it out. Okay, so that's a visual way. I'm going to do one more to tie in lesson 03, very first lesson of the year. So you all ready? Do I have this written down? No, I don't. So the next problem I want you to work is, let me go back to the graph to make sure I copy it down right. What if we had this? G of x equals x plus 3 over x squared minus x minus 12. Out of the same 3 types, infinite, I'm going to abbreviate, jump, or removable, this is not piecewise. Which of the 3 do I know is off the table? Will not exist. Jump is out. So it's going to be one of these 2 if it has them. Do you see division? Does this problem have division in it? What does this line mean right there? Division. What are you not allowed to divide by? 0. So to find your breaks, you set that equal to 0. Now, solving this, you have to factor this. The only way that I know how to do it is factor this. And so on lesson 03, I'll write that over here. On lesson 03, if you want to watch the videos later on, I teach you how to X method factor a trinomial. This is a trinomial. Have we already forgotten? There were steps. There are 4 steps. There's the greatest common factor step. There was the X method itself step, where you do your X, and you label your A, B, and C on this one. There was the 3rd step where we split the A power, sorry, blank there. And then we did bottoms up as the last step, 4th. Or I could say another way, divide by A, since we could divide by A. I'll write it that way. So those are our 4 steps. So let's look at it. Do I have a GCF in this denominator here, this trinomial? See any GCFs? Is there an X shared with all 3 pieces? No. This is like the coefficient 1, coefficient -1, and -12. Can any number greater than 1 divide into all 3 of those? No. So there's no GCF, so I move on. X method, we would label A is 1, B is -1, whoops, -1, C is -12. So you draw your X. Remember, we're looking for factors of A times C that add up to B. And those 2 numbers I listed as M and N, and I used a chart to help me out. So let's see, A times C is -12, and B is -1. So our goal here is to come up with 2 numbers that multiply to be -12 and add to be -1. And as I'm talking, a lot of you might have already know what the 2 numbers. Yeah, I'm seeing shaking your heads. Yes, we know what the numbers are. But in case you don't, a technique I use is I just use the number, the product, the 12, and just take the positive. I don't pay attention to the negative yet. And I write down all possible factors. I start at 1, so you have 1 and 12. 2, the next number after 1, goes in 6 times. 3 goes in 4 times, and that's actually the whole list. There's nothing else. Got them all. Which set of these numbers is 1 apart? 3 and 4. So our numbers are going to come from here. How do I make 3 and 4 become a -1? 3 minus 4. So those are 2 side numbers. Now that's the X method step. Again, you don't have to do the T-chart if you can just come up with those numbers on your own, but this is all just visual to help you out. Step 3, split the A power. Here's what that means. You go back up to the problem and you split the A power. This is the A, you split its power. So instead of it being a squared, it's going to become x to the 1st power. And then you put the side values from our x into the parentheses, x plus 3 and x minus 4. Step 4 is kind of like step 1. We divide by a, but you don't always have to do this. On this problem, our a is 1. And so what you'd be looking for is if you can simplify by the factor of a. But does dividing by 1 ever change any value? No. So dividing by a doesn't do anything, so I don't even need to do that. This is the denominator. So we did all that work, and honestly, we've gotten nowhere so far because we haven't actually found out any of these type of breaks. But when I rewrite the denominator, I can figure out what type of breaks I have. My denominator is the same thing as x plus 3 quantity times the quantity x minus 4. So I hear there's a removable. Which one gets removed?
The X.
Now remember, x is lied to you. So it's a removable where? Good, x minus 3. And what about this thing that stays around forever?
It's
It would be
infinite.
infinite at x equals 4 because it lies. All right, and I could show you the graph. That was a different problem. Done with this problem. I'm now on this one. We said at -3. Let's check it. -3. Yep, I got an open circle there. That means it's undefined. And then at +4, the graph breaks and go to infinity. If you want to check, just hit the gear, convert it to table, and you can type in -3. It says undefined. And also, we type in +4, undefined. Yep, those are our 2 breaks. All right, that was number 1. We spent a little time on that one, didn't we? Do you feel like you got that mastered now, maybe? Feel better on continuity? All right, I'm going to jump on to composition. This came from lesson 1.6. So on this problem, if you didn't notice, we went over stuff from 1.1, 1.3, and from 0.3 with the X method factoring. So that 3 of the 8 lessons we covered so far were built into those 3 problems I just worked, all under the heading of number 1. Number 2, this comes from lesson 1.6. Composition of functions. Now, I've been telling you the stack technique for solving f of g of h. F of g of h, I've been using stack, and I'm going to use stack, but I'm going to use a different set of terminology to help you out, because if you're still struggling today, chances are you didn't catch it the first time I taught it, so I want to say it a little differently. What's happening with finding f of g of h is, truthfully, it's a big time substitution. What we are doing is we are substituting g's equation into f, but before we even do that, we substitute h's into g. So it's kind of backwards of the way it's written. What happens is h gets substituted into g, and then that equation, g of h, gets substituted into f. I'll show you a visual. If this f of x I represented in blue, what you have is your f of x. But when you find f of g, what you're doing is saying, hey, let's remove the x from the problem, and instead of having an x here, sorry, eraser, come on, there we go. Instead of having an x there, let's replace that with g of x. But now when I look back at there, it's not just f of g though. This problem is f of g of h. So it says, well, even the x inside of g, we're going to take that one out, and we're going to substitute that one with h. And so ultimately, that's what we're finding, f of g of h. And I'm going to leave this off to the side because for Desmos, that's how we had to type this in to get the graph there. So when I do the visual, I'm going to need that. So that's what I'm finding. So let's go find these out, and I recommend using stack technique. The equation f is x squared plus 3 And then next, you write the G equation. I'll use a different color. G equals square root of x minus 7. And H is x minus 2. Oops, switch colors. Try again. H is x minus 2. So when I taught you how to stack, in what order do we go? Bottom or top to bottom or bottom to top? Bottom to top. Oh, you know what? I just thought of something. If you asked a question, it did not come through Zoom there. It kind of broke up. Here's another way of thinking about this I just thought of and never taught it this way. But basically what's happening is H's equation is going to get shifted into the place of x. And then that value is going to get shifted into the place of x. That's what's going to happen. H's equation is going to go into this x. G, that result is going to go into this is x. That's what's going to happen here. Okay, so let's first pay attention to this one. I'm going to take the equation h of x, and I'm going to substitute it in for this x. And I also, I like to, it says find domain. I like doing the domain at the same time. So what you look for are dividing by zeros or negative square roots. I mean, basically you look for division of x's and square roots with x's inside of them. For the domain, there's going to be 3 possible results: negatives, zeros, or positives. That's the type of numbers. There's 3 types of numbers: negatives, zeros, and positives. As we go through, we will eliminate. X minus 2, there's no division, there's no square root. So right now, I'm all reals. I substitute this up. And so when I substitute, what I get is g of h. G of h is going to be the square root. This x comes out, and it gets replaced with x minus 2 with the minus 7 on the outside, like that. And now I have a square root. So what does a square root eliminate? Are you not allowed to take the square root of negatives, not allowed to take the square root of positives, or not allowed to take the square root of zeros? Square roots. What's the square root of 0? What times itself is 0? 0. Okay, that's a real number. So we can do a square root of 0. What's the square root of 9? 3. We can take the square root of a positive number. What's the square root of negative 16? It's not negative 4, because negative 4 times negative 4 is positive 4. There is none. It's not real. We'll learn later on it's 4i, but for right now, it's not real. That's what I eliminate there. Okay, now I'm back over here, and I'm going to simplify this. Parentheses mean multiply, but there's no number to multiply, no coefficient. So I can take away the parentheses. So it's basically x minus 2 minus 7, which is the same thing as, if I owe one friend $2, I owe another friend $7, I owe a total of $9. That is g of h. To use perfect symbols, it'd be g of h of x, like that. That's what that is. So now that I have this result, what I'm going to do is take that result and plug it in to this x. So to get some clarity here, I'm going to move this work out of the way, and I'm just going to move over g of h this way. I'm going to take this result and substitute it here. So that's what I'm doing. And I'll move this out of the way so they're not confused by what it was. Oh, that's not what I wanted. Sorry, one more time. And then I'll quit wasting. Maybe not. I'll just erase it. Hope you had it down in your paper. Okay, so now I'm going to take this result and substitute this into x. So this goes in right there. So that means f of g of h would be the square root of 9, or excuse me, square root of x minus 9, that's going in right there, squared plus 3. I have a square root and a square. What happens to those two? Cancel out. And so we're left with x minus 9 plus 3, which means, when we simplify that, Again, to use the best type of writing, f of g of h, and those brackets of x would equal x minus, I owe a friend 9, but I have $3 in my pocket, minus 6. That right there would be your answer. Now we got to go finish up the domain portion. So you go to where we eliminated that part of the graph. It was right here in the square root. Oh, sorry, it was right here in this step. Okay. No, I can't hear you. Can you type into the chat what you're trying to ask? I'll answer it in a second. So I'm going to take the part that was in the square root and say it's got to be positive or got to be equal to 0. It's got to be positive or equal to 0. Positive or equal to 0. That means greater than or equal to 0. So our domain here is just a plus. When I add plus 9, I find out that x has to be greater than or equal to 9. That's the domain. There's a domain restriction here, which we talked about in detail on lesson 1.7 about domain restrictions. There it is. So I'm going to pause this for a second. Let's pretend we were taking a test. So I'm going to do this now digitally. Let's say this is your problem, and you have multiple choice answers. Let's say A says the answer is x plus, no, that's not the order I went, I'm sorry, plus 4, where your domain is x has got to be greater than or equal to, I think I did negative 8. Let's say answer choice B is that it's x minus 4, and your domain is that x has got to be greater than or equal to positive 8. Answer choice C is that x minus 6 has got to be with domain of x greater than or equal to 9, or that the equation is dx plus 6, answer, x is greater than or equal to negative 9. Let's say these are our 4 options. Now, obviously, we've already solved the answer. Which one's the correct answer here? We know the answer is C. But how you can do this graphically is like this. We could go over to Desmos. This is if you were taking a multiple choice test. And what you would do first is you type in your equations. Now, forgive me, I have f of 2. I just did that so that I could work the earlier problems without blowing up. And so what you would do, let me type all that away, and we'll be ready. Okay, you would type in the 3 equations as they were given. So our problem, I had f, g, and h. I'm going to write, that's all I did, is type those in, f, g, and h. You don't even have to look at the graph. Now, I got a problem somewhere. I didn't delete, somewhere I got a symbol that's not working right. Where is it? F, G, H. I don't know. Let's just type it in again. F of G of H of X. Here's my problem. Sorry. Now I got it. What happens is I have an answer that comes up when you graph these. Again, I don't have to look at the original graphs. I'm not paying attention to those. I will show you one thing, though, on the original graphs. Notice this red graph up here has all real domain. The purple graph has all real domain. G's graph, the square root, does not have all reals domain. Its domain starts at 7. But when we worked out the composition, the domain was at 9. So you can't even get domain necessarily from any of the 3 original graphs. It has to be the way we did it, the combination of the graphs. So I'm going to take these other ones off. We got this as an answer. Now, on the multiple choice, I said, let's just pretend these are your answer choices. And so you could just check by graphing, is this one the right answer? Is this one the right answer? Is this one the right answer? Or is this one the right answer? And so one of these 3, which we said it was C, is the right answer. Now, how do we know it's the right answer? It's right over it. Now, this is how you do a domain restriction in Desmos. You use these squiggly brackets. But even if you didn't know that, you could still just type in the normal equations and figure out which one was supposed to be the right answer by determining which one the composition lays on top of. So the answer had to be x minus 6. And you can see that it starts at that value of 9, the x value of 9. So that's how you can get that graphically. You take wherever the square root first showed up. So when we stacked, It did not show up on this step. It showed up when I substituted into G. And so when we simplified, we got x minus 9. That's where I took the number from. The first time the square root shows up with it simplified was x minus 9. So when I solved that, I said it has to be positive or greater than 0. And so we added 9. And that's why x is greater than or equal to 9. I'm going to do one more just with the number, though. I'm going to use easier equations. What if I gave you a problem like this? What if I said f of x is 3x minus 7, and g of x is 2x minus 4. Find g of f of, let's make it a 2. What would you do? Yeah. Yeah, so I can still use the same technique. You're right. You're right on. I can still stack, but basically what's happening is I'm going to find f of 2, and whatever that result is, let me actually put an x here. I'm sorry. Changing how I want to do this. And we'll do this g of x. 2x minus 4, and f of x is 3x minus 7. And so basically what's going to happen is I plug in the 2 here, but I'm not going to necessarily plug in a 2 here. I'm going to plug in whatever the result of f is, the y value, whatever comes out, whichever range value is produced, I'm going to plug that in to here. So we plug in a 2 to start. So when I do that, I get 3 times 2 minus 7. 3 times 2 is 6 minus 7, negative 1. So f of 2 equals negative 1. So what that means is I'm substituting in a negative 1 here. So a negative 1 goes in that spot. And so this would then turn into be 2 times negative 1 minus 4. 2 times negative 1 is negative 2. Subtract 4 more. Negative 6. And so g of f of 2, gosh, come on, 2 equals negative 6, where this 2 refers to the domain of g of f, and the negative 6 refers to its corresponding range output, and which would be the answer, by the way. The answer is negative 6. Okay, so there's that. Are you okay if I move on? So I'm trying to hit big chunks of a lot of different lessons. I don't hear any slowdowns. So we have covered, whoops, wrong thing. We have covered stuff from 0, 3, 1, 1, 1, 3, 1, 6, and domain came from 1, 2. That was lesson 1, 2 right here. When I did this, that's the beginning of lesson 1, 2, if you watch that. So I've now covered the first 4 lessons and 1, 6. So we're missing 1, 4, 1, 5, and 1, 7. That's what I haven't covered yet. So let's move on. 1, 4, 1, 5, 1, 7 is what I've not hit yet. So this one, unfortunately, also comes from 1, 3. The problem asks us to describe the end behavior. I'm going to do more than that. I'm going to describe the behavior. Oh, wait, I didn't see the and. I'm sorry. I'll do the end behavior and the behavior of f around its discontinuity. So this is the exact same problem we looked at earlier. Exact same. What we talked about is discontinuities occurring at x equals negative 12 and x equals 1. That's where our discontinuities occurred. When we talk about behavior, we're finding limits. And here's what I want you to be abundantly clear on. This graph has 3 pieces. For pre-cal's sake, every piece of graph will always come with 2 limits. So I'm going to say that again. Every piece of graph comes with how many limits? 2. Every piece of graph comes with 2 limits for pre-cal's sake. And this graph has 3 pieces. So if the graph has 3 pieces, how many limits would we write? 6. Good math there. What do we do? If there was 3 pieces, And every piece has two limits. 3 times 2 is 6. Okay, let me tell you how the test will work. The test, because that's what we're doing right now, is we're test reviewing. I'm going to give you the x value on all of these. Your job, and I won't be putting it right next to the graph, your job is to determine what does that x value mean, and what do I put for the y value. So this is how the 12 limits would look, or 12, the 6 limits would look for you if you were completing this test. If you had to do any one of the 6, your problem will be randomized. You never know what you'll get. Man, it takes a while to write this 6 times. And then finally, last one. So there are 6 limits. And I would give you that information. Your job would be to fill in what goes for the y value all the way across. So in black is what you'd be given. Although I would not give you that writing right there. So it would look like that. Now there's really 4 responses you need to think through. Does the graph travel up forever? Does it go down forever? Is it getting flat forever? Or is it just stopping at a point? Okay, I'm going to do this one last because it's kind of the hardest to tell. I'm going to start this one. Is it going up forever at this break? Is it going down forever? Is it going flat forever? That means horizontally. Or is it stopping at a point? It's going up. And so what y value represents going up? An infinity. And so that would be, if you were given this, by the way, what this means is it's the break of -12. Actually, you know what? I'll tell you what this means in one more second. Let's do this bottom one first. What happens on this side of the break? It goes down forever, which is negative infinity. Now, I put a minus on this one and a plus on this. The reason why, if you think about functions, every function has to have unique x's. You can't double up x's. What's happening on my x's if I don't put the minus and the plus? What do you notice about my x's? If I did not put that minus and the plus, they'd be equal to each other. They'd be exactly the same. You're not allowed to do that. And so the minus and the plus just tell you it's the piece on the left side or the piece on the right side. So the piece, here's the break. That's on the left of the break goes up. The piece that's on the right of the break goes down. That's all it tells you. All right. So on this one, I have the same thing. I have duplicated x values of 1. So I put a minus and a plus just to tell me, am I looking on the piece that's on the left of it or the piece that's on the right of it? So the piece that's on the left, is this going up forever, down forever? Is it going flat forever, or is it coming to a point? It's coming to a point. And what is that y value? It's 0. I don't know if I can even zoom in anymore. Yes, I can. Look at that. What's that y value right there? It's a 0. And so for you in the test, you'd fill in a 0 for that one. Let's talk about the other break. On this one, does this go up forever, down forever, flat forever, or does it come to a point? Point. And what's the y value at that point? 2. Now let's do this in behavior. As this goes off the screen going right forever, so here's my x, it's going more and more right. Is it going, that's why it's a positive infinity, that means it's going forever to the right. Is it going up, down, flat, horizontally, or to a point? It's also going down. And so we would put a negative infinity there. Which leads me to this last one, and this one's a little tricky. I should have zoomed out one more time. Because I didn't zoom out, it's kind of harder to see. But on Desmos, if you zoom out, this graph turns and goes like this. And it basically stays flat, which I didn't draw very flat. So I'm going to show you here. It's basically flat on this line there. So what's that y value? 2. And so on this one, the answer would be a y value of 2. Now, just to distinguish, when it says in behavior, it's specifically talking about the one that goes to the left end of the graph, going to negative infinity, and the one on the right end. When they say in behavior, they're talking about the one that's going for x going to negative infinity and x going to positive infinity, those 2 limits. That's the in behavior. And the behavior around the discontinuities are these other 4. They're the ones on the breaks. just to distinguish that. Okay? You want to do another one of those, or are we good? Now, I don't have anything from less than 1,4. I do want to point out 1,4 was over maximums and minimums and zeros. I do want to point out this is not a minimum there. For graphs to have a minimum or a maximum, you have to have like basically a parabola-looking piece, like a hill or a valley. That's not ever a valley. Doesn't ever come back up, nor is it a hill. This one's not a hill, so there's no maximum on those. So you would have no extrema. That was less than 1,4. I do have one picture. I'll skip while I'm talking about that. I'm going to skip ahead. This one would have an extrema. What would you call that point right there? A minimum. Is it an absolute minimum or a relative minimum?
Relative?
Is this the lowest point on the entire graph or just the lowest point in the area? Area. So it's a relative or local. Relative or local min. Okay, I just wanted to throw that in. Otherwise, I probably would have forgotten because I don't have anything on less than 1,4. But there's that. Okay. Y'all ready to transition to transformations? Okay, I'm going to pause this recording for a second. Now let's take a look at lesson 1.5 stuff. So lesson 1.5 was all about transformations. And I gave you 2 rules. The first rule I used an acronym, HIVO. Where if I, just a reminder what an acronym is. If I said NYC, what's the first thing that comes to your mind? New York City. That's right, it's an acronym, New York City. That's what this is, an acronym. It stands for horizontal is inside. Horizontal is found inside. Vertical is outside. And I just do the capital letters to separate them. Vertical is outside. Okay, so another way of saying this is that the x values are found inside. X's are inside. The y's are outside. Rule number 2 says that inside lies and the outside tells the truth. Said another way, your x's lie, your y's tell you the truth. And this was my joke that I made, saying that your x's, you break up with them because they're always lying to you, and your y's, you marry them because they tell you the truth. Obviously, there's a little play on words there. This is supposed to be a real x. X's lie, and the y's tell the truth. And so when we look at transformations, there's really just a couple different things you're looking for. Negatives do reflections. Multiplication of values either stretch or shrink. And adding or subtracting values shift a graph around. They translate it. So I'll say that again. Negatives reflect. Multiplying by values either stretch or shrink. And adding, subtracting shifts it. And so what we're looking for really are things, first off, rule number 1, if they're inside or outside. And as a reminder, what do I mean by that? X's are located on the inside. So this would be referred to the inside. Anything outside of the parenthesis, so anything out in front or behind would be the outside. So when I ask you something in or out, that's what you're paying attention to. You'll find whatever the brackets are that surround the X, that would be the inside, and everything on the outside of those brackets would be the out. So here on this problem, I see 1, 2, 3 transformations. The cube is the shape. That's not a transformation. It's going to be an S curve. But I have 3 transformations. What is that 10 do? Is it inside or outside? It is outside. So if it's outside, guess what it is? It's going to be vertical. I'm going to use these words because that's what your test uses. It's going to say vertical or horizontal as we go. So it's going to be vertical. And that 10 there, what's it doing mathematically, specifically to where those parentheses with the X? Is it adding, subtracting, multiplying, or dividing? Is that adding, subtracting, multiplying, or dividing? It's multiplying. So anytime you multiply by 10s, when you multiply a number by 10, it always grows larger. It gets bigger. It stretches. That is if it's telling the truth. Now, do vertical ones tell the truth? Vertical or Y's? Do your Y's tell you the truth or do they lie to you? They tell the truth. So this is going to be a vertical stretch by a factor of 10. That's what happens first. Now the next piece is this -4. Now that -4, is that on the inside or the outside? That's inside. So if it's inside, guess what it is? Horizontal. So that's what HIVO stands for. Horizontal inside, vertical is outside. So this is inside, and inside always lies. So if you think about -4 on the x-axis, it's to the left 4 units. But because it lies, this doesn't go left 4 units. This is actually going to shift right 4 units. That's what's going to happen here. It's going to, because it lies to us. So we actually go to the right 4 units. I'm sorry, right 4 units. And then here I have one more on the outside. I gave that away. I accidentally said what. Is that inside or outside? That's outside. So if it's outside, guess what? It's vertical. And if it's vertical, it tells the truth, or outside, it tells the truth. So if you think about vertically, the +3 would be there. So it tells the truth, so I just go up 3 units. Vertical shift up 3. So again, anytime you add or subtract, it's a shift. Anytime you multiply or divide, it's a stretch or a shrink. Specifically, it all has to do with if the number's bigger than 1, it's a stretch. If it's less than 1, it's a shrink. And then if there's a negative, which this problem did not have, but like a negative up front, that's a reflection, okay? So that's what happened. Now let's look at the graph. I have this graphed already. And so for this first graph here, take this away. I no longer need that. So now, that's what a cubed graph normally looks like. We said it should go right 4, down 3, and be stretched vertically. And so there it is. This graph, if you notice from vertex or from center to center, this one is shifted right 4. If I can't seem to find it, there it is, up 3, and it's vertically stretched. Now, at this stage, I'm going to turn on my camera so you can see me. When you think about a graph being vertically stretched, so classroom, eyes over here for a second. The way this works, when I teach 1.5, if we're in person the whole way, I like to bring a balloon to class and actually squeeze a balloon different ways, because stretches and shrinks were kind of like a balloon if you stretch them and shrink them. What do I mean? This is a vertical stretch. So if you think of, here's your balloon, and you turn it vertically. So I got my balloon with my hands vertical, and I start to stretch it vertically. I want you to visualize what happens to that balloon as you pull it this way. It looks also like it gets thinner this way. Graphically, that's what happens when we vertically stretch. You see how this graph, how wide it looks around, we call that a point of inflection. You see how wide that looks in there? Look how much narrower this one looks. It's because it got vertically stretched, so it made it look like it's horizontally compressing. So they're not the exact same thing, but they appear visually to the eye to be the same thing. Does that follow my illustration there? Okay. Let's take a look at the next one. So I got 3 examples. There's this one. Let's try this one. Again, I got the same rules right up here. And so this time, I see all these minus symbols. But this front one's different. I don't read this as minus parenthesis. How do you read this? Negative. And so whenever you have a negative, that's, what is it? It's a reflection. Okay, so this front one's going to be a reflection. Negatives reflect. So it's a reflection. Now usually though, I ask, the first thing I do is it inside or outside? Outside. So outside goes with the V. What does V stand for? Vertical. It's a vertical reflection. Now, one thing that's tricky with reflections is this. So each transformation, as we get more complex, can come up with some little tricky things. So you get used to them. A vertical reflection means whatever is up is going down, and whatever's down is going up. On the test, it's going to ask, and I'm trying to prepare you for ACT test, SAT, it's going to ask you over which axis is actually how way to write it. Which axis do you actually reflect over? Over the x-axis. Now, this is tricky because it's a vertical, which what letter do you think it should be if you think of vertical? We would think normally y, but it's talking about which one are you going over. We're reflecting over the x-axis. So that's actually how it's going to be written. Next transformation, I'm going in, is right here. And notice this problem is a 2 up here, so it's not going to be an S-curve. What's a squared graph look like? Parabola. Yeah, this one's going to be a parabola. Okay, now here, is this inside or outside? Inside. So that means if it's inside, it goes with the H. What does H stand for? Horizontal. And by the way, reflections don't lie. There is no lie on that. So reflection is just going to be a normal reflection. I forgot to say that. So here we are. Does this lie or tell the truth? It's going to lie. So anytime you add or subtract, it's always a shift. So it's not going to shift to -5. It's going to shift to +5. Which way is that for x? To the right 5. And now finally, change colors. -3. Is that inside or outside? Outside. And notice I said here -5, and this is -3, not negatives. I would just say -5, -3, which means we're not reflecting here, we're just shifting. You said outside, so if it's outside, guess what? What's the V stand for? It's a vertical. Anytime you add or subtract, it's always a shift. Outside tells the truth, so -3 means directionally down 3. Starting to feel like we got that pretty good? Are you ready for how you get tricked? There's a trick that comes in with horizontal stretches and shrinks. Oh, I didn't show you the graph. Show you the graph really quickly. Let me change this now to a square. And this is the graph. Notice it's been reflected over the x-axis. It's been shifted right 5, just like we said it would, and down 3. Okay. How transformations get tricky? I know 2 big tricks. The reflection, because they ask you over which axis, and that can be tricky. You just have to think about which axis do you actually cross over. That's the first one. But you get used to that one when I show it to you a bunch of times. The one that routinely seems to rear its ugly head is when you have a horizontal stretch or shrink. This is where problems occur for many students. And so I'm telling you right now, this is a harder problem. This is no longer easy, this is a harder one. Let's go through our values. Would you call this -5 times the square root, or would you say -5 times the square root? How would you read that? -5. So if it's a negative, guess what it is? This is a reflection. Is it inside or outside? It's outside, which means outside is vertical. If it's a vertical reflection, that means what was up goes down, what was down goes up. Which axis did we just cross over when I reflected that way? I'm going over the x. So over x axis. What I just did there, sorry, I wrote the should go in this order. What was up gets shifted down. What's down got reflected up. I said shift, I meant reflected. And so you're crossing the x-axis to go from up to down. So that's why it's over the x-axis. Okay, next. I have a 5 here. That 5 is multiplying. Anytime you multiply, what's going to happen? Stretch or shrink. I'll just leave it as a S for now. Is that inside or outside? Outside is vertical. We got to determine, is this a stretch or shrink? When you multiply by 5, it's outside, so it's telling the truth. Does the number get bigger or smaller when you multiply by 5? Any number, 2 times 5, 10 times 5, bigger. So that means it's a vertical stretch because it's telling the truth. By factor, 5. That means you multiply it by 5. That's what that means. I'm going to skip the inside just for a second. I'm going to go to the very end. What does this do? Vertical or horizontal?
Vertical.
It's vertical because it's outside. Anytime you add or subtract, it's always a add or subtract always shifts or translate. And outside tells the truth, so plus 4 moves it up 4. Okay, the tricky part. Many students are going to see this and they're going to say, oh, that is inside, so it's horizontal, which that part's correct. They're going to say, oh, we're adding or subtracting, which is a shift, and that's correct. Where they're going to make a mistake is say it's just a shift of 2 units. Now, why is that a problem? Well, it's because of this right in here. This is also inside, and it says it's a horizontal because it's inside. It's either a stretch or a shrink because I'm multiplying by 3. But inside, does it lie or tell the truth? I put just shift 2. I meant to say shift. Which direction is that going to go? -2? It's going to lie and go right 2. That's what many students are going to say. And by the way, that's wrong right now. We'll correct it in a second. This is going to be horizontal, either a stretch or a shrink. So I'll put an S. Now, inside lies. So normally when we multiply by 3, the number gets bigger. We want to divide by 3. What does that do to a number? Anytime you divide it by 3, it's smaller. So it's going to be horizontal shrink, or compression is another name for it, by factor. And to say divide by 3, the way you do that is divide by 3. Since there's no number up top, you put a 1. It's like saying this is 3 over 1, so that becomes a 1/3. You just flip it. If it's a fraction, just flip it. Take the reciprocal. Okay, so now that I've done that, I'm going to come back over here. What this means is every x value gets shrunk by a factor of 1/3. So it's not going to go right 2, it's going to go right 2/3. You multiply it by that 1/3. So this is actually going to get shifted right 2/3. I know it's tricky, but that's what happens. I'll prove it to you on the graph. I told you that is the trick. Just watch this video again over if you need more help on this one. But on this graph, I think it was a square root. Let me go back over. Square root of x this time. All right, I'm telling you it's going to get shifted right 2/3. So notice here is 1, here is 0. This graph originally starts at 0, 0. It gets shifted right 2/3, and it goes up, it looks like 4 units. Let's check that out. If I put the point 2/3, comma 4, is that the start of the graph? You bet, it went right 2/3. Now, not only that, we said it was vertically stretched and horizontally shrunk. Remember, vertical stretch and horizontal shrink? So what that means, using the balloon, a vertical stretch and a horizontal shrink is going to doubly affect it. It's going to make it look like it's really stretched this way or shrunk this way. And so on the graph, this one has a large difference. If you notice how much quicker it's going down than the other one went up. It's like that balloon being squashed in 2 different ways that were agreeing with each other. I was horizontally shrinking it in, that balloon, and vertically compressing it, stretching it out. So it got bigger a lot faster. It was shifted right, and it was shifted up and reflected over the x-axis. You're right. Finally, domain and range. So again, this was lesson 1.4. I wanted to throw that in. 1.4, domain and range. So if you're going to find domain and range from a graph, whoops, wrong thing. Here we go. I used a technique earlier this year. I called it trash compactor technique. So I'm going to help you find the domain and range using what I call trash compactor technique. That's because when we look at this graph, many times we get the domain mixed up with discontinuities because they work together. Now this graph has discontinuities. What type of discontinuities are these? Infinite, removable, or jumps? Jumps. Very good. We have jumps here. And we get that confused with domain. We think, well, that discontinuity, I need to list it in my domain. Not necessarily. So to help you out, the technique I use is trash compactor, because what we do is we strip away some of the discontinuities so that you can see what is just the simple domain of the problem. And so when I do trash compactor, think of if you leave out your trash and the garbage truck comes by, throws it in there, and then it smashes it to take up less space. That's what's happening. And so I'm going to treat this first piece as, I'll call this the red piece. What I want you to envision is this this arrow is going to get smashed down, and I'll put it right there. You just smash it directly to the x-axis. This open circle directly to the x-axis. It's connected by a curved line. Well, when it gets flattened, it's going to be a straight line now. So there's the domain of the first piece. That's the domain. This red line represents this curve up here for the domain portion. This next one I'll do in blue. So again, smash it to the x-axis, close dot, open dot. It's solid in between, so it's going to be solid like this. And then finally, the blue represents the domain of this piece. Now let's do green here. I'll smash, arrow, it's connected solidly, so I'll connect it solid. So this color right here represents the domain of the graph. And so though the discontinuities look like this graph was broken, what can you tell me about the actual domain of this graph? It's unbroken. Everything's filled in. The open circles get filled in with closed circles. So guess what the domain would be then? Negative infinity to positive infinity if you're using interval notation. If you're using inequalities, you would just say x is all real numbers. Now there's the domain. And again, we call this a relative minimum because there's lower parts on the graph. Absolute would be if it were something like down here. Then it would be an absolute. Okay, now I'm going to strip this and I'm going to do range. So range deals with the y value. So domain dealt with the x. Now we're going to deal with the y. So I'm going to take my horizontal lines and make them vertical lines to help our visual representation. So if you put your imagination caps on here and just imagine this being smashed to the y-axis, how this graph would look. So the first piece was red. I have this open circle here. I have an arrow right here, but what's a little bit different when I connect this one is you see how that curve goes down below? Now I put a solid dot there because it's a solid line. So it would go down to like this solid dot. So it goes down and then it goes back up. But this time when it goes back up, since it's a solid line, this would be like a closed circle. It fills it in. So this is like a closed line coming from this point up to this arrow. Now I go to the blue piece. It says open circle, oops, closed circle. Oh, wow, that was really ugly. Let me try that one more time. Undo, blue. Connect like that. Yeah. No, it continues on forever. Yep. Now this one though is a little different. This does have an arrow, but when it smashes, it was going directly horizontal. So when I smash it in, it just becomes a dot. Now, even if this was an open, this would be closed here because all of this is considered closed dots. So I want you to know that. That would be right there, closed all the way through. And it just stays on -6. So is our range this time going to be all reals? No. I can see there's a break here, and this open spot is going to be an arrow. So that's not a break, but I have two open areas. So where does this range start? You go bottom to top. -6. Since it's only -6 and nothing else, you just write a -6 with a bracket. You don't do (6) or anything like that. Just -6. I'm doing interval notation first. Then I have a break. We represent breaks with a union. Closed circle on -3. So again, another bracket because it's closed. To infinity. Parentheses. Infinity always gets a parentheses. If you want to write these as inequalities, you would either say x equals -6. Union means or. X is greater than or equal to -3. You could have said -3 is less than or equal to x if you wanted to. I just wrote it that way. This is the smaller number, this is the larger number. You don't have to write infinities in that simple. So that's how you would do that problem. So I covered everything but lesson 1.7, and that's what we spent the whole time on last lesson. Just in a nutshell, 1.7's inverses. And so if you needed help on inverses, again, just to give it to you in a nutshell, all that you would be doing is switching your x and y and solving from there. I will show you how you can do a graph. So like if we want to know the inverse of, what's the inverse of, let's call it 3x plus 5, find g -1 of x. What that means is find the inverse. That's what that symbol means. And so I'll do both algebra and graphic. If you do algebra, remember g of x is your y. And so the way you'd solve this, instead of saying y equals 3x plus 5, the first step is you switch x and y. And then you solve for your new y. So what would I do here to solve? So starting here is where I'm finding inverse. As soon as you switch x and y, we're now working on the inverse. So this is the inverse equation, but just not in standard form. Standard form is when you solve for y. So I hear -5. I agree with that. And this is less than 1.7. So x minus 5 equals 3y. And last step, divide by 3. And now we've solved it for y. Once you solve it for y, you use this terminology. And so you'd say g -1 of x equals x minus 5 all over 3. As by way of reminder, if I restricted this domain, let's just say I said that this domain, I want to restrict it for whatever reason from 0 to -infinity. That means this range would be from 5 to infinity. If you're wondering what I just do, I just made up the 0, but when I plug it in, I get my range. 0 times 3 is 0, plus 5 is 5. That's my range. What would happen for the inverse, by way of reminder, is the domain and range would switch. So this domain is now 5 to infinity, and this range would be 0 to infinity. Because if you switch your x and y's, the domain and range also switch. Now, I just threw this in on my own. That was not part of the problem. It's not like I had to solve it. I just made that up. And now I'm going to show you this by way of graph. If I, man, those wrestlers. G of x equals 3x plus 5. There's your equation. The inverse, what you would do is you would type, instead of y equals g of x, that's what we normally think of, you switch your x and y. So x equals g of y. That's going to be the inverse, and test our answer. What do we get? X minus 5. Oh, sorry. X minus 5 over 3. Check it. Is it the same? Yep. And if I gave you that domain restriction earlier of x greater than or equal to 0, then for this to be right, I would have to end up with the domain being x greater than or equal to 5, because it switches, and now they match up again.